Hi, I'm Adit Gupta, and I am a PhD student at Drexel University under the advisement of Dr. Chris MacLellan. And this talk is regarding designing teachable systems for intelligent tutor authoring. So, in this talk today, we're going to be talking about intelligent tutoring systems to give a brief background on difficulties, progress, and so forth. We're going to talk about this new concept of teachable AI. We'll explain a recent framework that's helped our work, the natural training interaction framework. We're going to talk a little bit about our approach to using this framework for tutor authoring experiments with the Wizard of Oz experiment. Um, we'll also explain a variant of the Wizard of Oz experiment known as the dual-sided limited perception Wizard of Oz experiment. And lastly, we'll share how we use this variant experiment to with the natural training interaction testbed we engineered, and also excitingly share some of our progress and share some of um, what we learned from real human experimentation. So, first thing, intelligent tutoring systems have, what are they? They're a type of computerized educational technology that tutor students on problems by providing additional interaction, like student feedback, next step hints, demonstration, and so on. And over the last decade and more, these intelligent tutoring systems have consistently showed um, student improvement and improvement of educational outcomes when they're used alone or in combination with other methods. So these tutoring systems, have been shown to be effective. And an example of a tutoring system on the right side, we can see Alex. It's a cognitive tutor. Um, it's quite popular in K-12, and these tutors, while effective, they're incredibly burdensome to make. There was a study in 1999 by Murray, and essentially the benchmark was authoring a intelligent tutoring system. It may take almost 300 hours of development time for 1 hour of instruction time. So we know that these tutors are effective for um, improving student outcomes. However, they take a long time to build. So now this is a problem, and recently there's been um, certain advancements to authoring intelligent tutoring systems. As an example, there's the cognitive tutor authoring tool example tracing, and sim students authoring by tutoring that have actually shown a reduction in authoring time by as much as 4 times. And this was a study um, by Elvin in 2009. And so there's tools and techniques that are coming out to help reduce the time it takes to author these tutoring systems. And another example of such a technique is the apprentice learner architecture, which essentially builds upon prior sim student work to essentially provide a method to be able to essentially promise superior performance over these existing models. Um, but one of the missing pain points still is these new methods are not being tested by with real humans. So ideally, what does that mean? We want to be able to create tutor authoring with ways that have been tested by real humans. And so, as simple as that, when you want to create tutor authoring mechanisms, you have to understand, what is teachable AI. So, over the last 10 years or so, there's been a lot of applications of teachable AI. As cognitive systems have become ubiquitous, there's technologies like Google's Teachable machine, as we can see on the right side here, that have come out, and these systems essentially allow you to create a model specifically by teaching it, by a model for image detection, for speech detection, for different kinds of applications like that. And while these teachable AI models are becoming more prevalent, they still have a gap with tutoring systems, specifically these intelligent tutoring systems. So, in our research, in our line of research, what we do is we use the natural the framework, the NTI framework, to better understand what makes an interaction natural, and then actually use that to build more effective tutor authoring systems. So that gets us into the NTI framework, the Natural Training Interaction Framework. And so essentially, to better understand the Natural Training Interaction Framework, we must first talk about what makes an interaction natural. So, as we saw in Chris MacLellan's 2018 paper, naturalness can be derived from four characteristics. First is they must support the goal of the user. Second is they must do what the users expect. Third, allow the users to work the way they want. And fourth, to leverage users' experience to minimize training. So this is actually a pretty common HCI methodology that we want to piggyback off of. And as we understand the natural training interaction framework, it actually breaks down a cognitive system training interaction into four characteristics. And these four characteristics are knowledge, patterns, types, and modalities. So in the context of an interaction, what that means is, the goal of any interaction between a human and an AI agent is to change the agent's knowledge. So whoever is changing this knowledge, they must use some kind of instructional pattern. And whoever, as this pattern is being changed, you must try to use or engage in several actions or several types of interactions. And this might include command, acknowledge, inform. And then lastly, in these interactions, they're done by different modalities. So to talk a little bit about these different characteristics, knowledge comprises of beliefs, goals, concepts, experience, skills, and dispositions. Patterns comprise of passive learning, operant conditioning, direct instruction, apprentice learning, after action review, collaborative learning, and so forth. Types may include demonstrate, reward, spotlight, inform, acknowledge, and so forth. And the modalities that may be used in an interaction may be command line, they may be a control device or a GUI or a sketch or an API or speech and so forth. So the natural training interaction framework essentially helps us break down an interaction into these characteristics to help understand the transfer of knowledge from, in this case, a human to an AI agent. So one of the problems, though, is as we use the NTI framework, we must try to figure out, how can we transfer this knowledge to an AI supported tutoring system. But for that, we must build an AI driven tutoring system. And now building an AI driven tutoring system, again, is going to cost us time, it's going to cost us money, and so forth. And again, we don't know which kind of tutoring system may be optimal for human interaction, specifically tutor authoring. So that's where the Wizard of Oz experiments come in. And created in 1999 by Dahlback, these Wizard of Oz experiments essentially let us use so they're interactions where subjects interact with a computer system that the subject believes to be autonomous, but they're actually operated by an unseen human. So as we can see in this image, there's something going on here where they're speaking with this device, which looks like to be an Alexa device, but instead of an AI-powered Alexa, it's actually another human that's actually corresponding with interactions. So now these Wizard of Oz experiments help us save time and money, but one of the problems again is these Wizard of Oz experiments aren't meant for prototyping learning systems. So how do we combat that? We actually built a variant of the Wizard of Oz experiment known as the dual-sided limited perception Wizard of Oz experiment. And essentially what we did is we replaced the experimenter or the behind the scenes with another naive participant. So instead of an experimenter and a participant, we essentially have two participants, and they have a perception filter where they can engage with one another. So this is a good segue into describing our experiment and what we did. To understand what makes these interactions natural, we must first learn from teachers teaching a task to a student. And in our case, what we did is we built a pipeline and we engineered this NTI testbed where we are able to pair participants randomly we're able to connect them and give them a role randomly as a teacher and a student, and we're able to let them interact with one another. And so the idea behind this interaction is that in our particular experiment, we had different types of interactions. So, as an example, for patterns specifically, we had the reward pattern where the student would move, and the teacher essentially had to approve it or disapprove it. We had the demonstration pattern where the teacher would essentially demonstrate a task, and the student was tested on that specific task. And in our case, it was, for example, moving a green cross on a blue star. We had the apprentice pattern, which was a combination of reward and demonstrate, where the student could make a move, the teacher would approve or disapprove it, and the student could also request a demonstration. And then lastly, we had the chat pattern, which is, there's no demonstrations, but the student and teacher are in direct communication via chat area where they can talk with one another and they can transfer knowledge that way. So in this pipeline that we made, it's actually task agnostic. This is essentially a pipeline to be able to test how two participants can interact with one another in a sort of a teaching task. And because of current global circumstances and not being able to do so with real humans, we utilized AWS's Mechanical Turk to connect these participants, to fine tune and connect them randomly, pair them as a student or teacher, give them instructions on what the task is, what is the task that this teacher must explain to the student, and then actually let them go through doing the entire task. What we then do is we actually have a questionnaire for both the teacher and the student after the student has finished the testing portion for what they learned from the teacher. And then we ask them a whole bunch of questions on their experience. Now, these patterns, just to talk about the reward, demonstrate, apprentice, and chat pattern, what do they mean? So we've actually mapped out the patterns to what kind of technique they might mimic. So as an example, if a teacher provides feedback, that may actually mimic reinforcement learning, a machine learning methodology. If a teacher provides examples, that is something like learning by demonstration. If a teacher provides language-based guidance, chat, that's learning by language. And our goal really is to figure out really novel machine learning methods that are optimized for tutor authoring. So that is sort of where the dual-sided limited perception WAS experiments come in, and being able to do so remotely using AWS Mechanical Turk. Understanding this data is essentially going to help us build tutoring systems that humans can interact with naturally. So let me show a demo of how these work together. What we can see is on the left side is the student, the right side is the teacher. The student actually makes a move. On the right side, the teacher either approves or disapproves it. As we can see here, if the student is going in the wrong direction, the teacher can disapprove it. And what the student is trying to do is they need to pick up the green cross and move it onto the blue star. And the teacher actually approves it or disapproves it. So in our experiment, we had multiple iterations of this, 3 to be specific. There were 3 training interactions where the teacher would interact with the student 3 times using the reward, demonstrate, or apprentice, or chat. And they would help pass on this knowledge and the knowledge essentially is you need to move this green cross onto this blue star. Now, when this knowledge is passed, the student is then tested, and they get a few 3 to be specific testing phases where they're asked to repeat that task before they're taken to the survey portion. So now in the survey portion, both the student and the teacher are asked both qualitative and quantitative questions. So as an example, they might be asked on a scale from strongly disagree to strongly agree if the student did the task correctly, or if the teacher taught correctly. Other things like, did the student only provide few examples, or did the student complete the task quickly? Did the student, was it natural or intuitive to instruct the student? And we're getting all this data from all of the different patterns that are employed in the experiment: reward, demonstrate, apprentice, and chat. And what we can actually do once we have enough data is compare amongst those patterns to see things like which pattern was most natural, which pattern was quickest to transfer this knowledge. And we also have these open-ended questions where teachers and students can describe, what was the task you were required to teach, or what was the task that the teacher taught you. And some of the data, what we've been seeing is, I was required to move the green cross on the blue star. And that essentially means they understood the task from the instructions. They were able to pass on that knowledge to the student, and then the student was able to understand that knowledge from the teacher. So this is some of the data that we're collecting from our survey portion. And just to go over a little bit more comprehensively, the data we collect from something like the chat pattern. Now, the chat pattern is something where there's no demonstration or reward. The teacher and student actually are able to communicate with one another via chat area. The student is able to move around the test bed or the game space, and the teacher is able to either say, no, don't do this, or yes, you're doing the right thing, keep doing what you're doing. And we found some really interesting data from our preliminary results. And, to summarize, what we found was most interactions or most messages were, under 3 words. As an example, yes, go ahead. They weren't full sentences like, hey, you need to keep going north until you find the green cross, and you need to then put it on the blue star. What we also found is a lot of, when explaining this task, it was very sequential. So they would say something like action 1, or go to the triangle, or go to the blue. And some of the feedback that we got from the survey was that the teachers were often explaining sequentially and not really passing over this end goal of take the green cross and put it over the blue star, which was interesting. So, this is some of the qualitative data we're able to get from our chat pattern. And as we run more of these experiments, we will be able to better understand what are the communication patterns when teaching a task. So that sort of brings us into lessons learned from our pilot experiment. We've run two batches of these experiments with about 40 participants each. And in these batches, per batch, there's about 20 teachers and about 20 students. They're connected with one another. And what we've noticed is, lessons learned is, in order to get high quality data, we must make sure that the pairing process is seamless. So what ends up happening is, using AWS Mechanical Turk, teachers will often wait in a student room, or participants will either wait in a student room until another participant is matched, and then they'll be given a role of either a teacher or a student. And so this actually leads us to another lesson learned, which was, it's very important to be very meticulous in logging. So since we started, we've actually built enhancements into our test bed to be able to record everything from the timing of how long they spend per instruction page, to how long is their testing period, how long is the training period, how long is survey, etc. And we're also using some advanced analytics tools like Inspectlet to be able to understand heat maps to when students and teachers are passing this data, where are they clicking, and so forth. So, the longer term of this research path helps us understand, what are the interaction patterns that are needed for teaching an AI system naturally. Additionally, we may want to then see, can we actually build a teachable AI agent that supports those patterns? So if we go back to some of these, this pipeline is task agnostic, meaning we can swap out our current game for another game, but our perception filter essentially lets us control the interaction between the student and teacher. So because in our early work, we were able to test the demonstrate, reward, apprentice, and chat, getting more data will help us understand which pattern specifically is optimized for building tutoring systems. So now when we find out what's optimized for building these teachable AI agents for tutor authoring, we will be able to then compare how human-to-human knowledge transfer compares to human-to-AI knowledge transfer. And those are the 3 research questions largely that's guiding our research. And really, as next steps, what we aim to do is we want to continue to get more data points, run more experiments of 40 to maybe even up to 100 participants, where each participant is paired with another one, and they are able to interact with one another with a particular interaction pattern. As we start aggregating a lot of this data, our goal really is to get about 20 to 30 full completed interactions per pattern to help us better understand or make conclusions from um, our data in terms of intuitiveness, in terms of which pattern may be quickest, easiest, and so forth. And with the NTI testbed that we've engineered, we can actually swap our game for other patterns. So ideally, we'd want to figure out what are the patterns that are needed for a particular type of knowledge transfer, or a particular type of task, and that's the direction that we're heading into. So with that, thank you for listening to this presentation on uh, authoring or designing teachable systems for intelligent tutor authoring. And I would love for you guys to connect with our lab, which is the Tail Lab at Drexel University, the Teachable AI Lab. And you can find us at tail.cci.drexel.edu. And with that, thank you very much.